Okay, so we're going to start looking at some integration techniques. And up until now, we've had substitution. That's been about it. But now we're going to look at integration by parts. Now, integration by parts will enable us to do things like unravel the product rule. In other words, when we differentiate something, remember, we take the derivative of the second times the first plus derivative of the first times the second. Well, when we integrate, we kind of need to unravel that. So you can think of integration by parts as our attempt to do that. So in other words, let's think about if we've got a function. Let's see here. Let's suppose we've got a function, and a product, and let's suppose that u is a function of x and v is a function of x. And let's suppose...
So does it record audio too?
Yes. Okay, so so let's suppose we've got a function, or a product of functions. And I'm going to use this notation. I'm going to denote the derivative this way. In other words, I'm going to just use d to denote derivative. Really, we're using this differential notation. I'm doing a little bit of a shortcut to it, but if the notation bothers you at all, let me know, and I can go back and kind of show you where it comes from. But let's just suppose I want to differentiate this product. Well, you know we're going to take u times the derivative of v, right? We'll just denote it that way. Plus the derivative of, well, v times the derivative of u, right? That's the product rule. Okay, everybody see that? Now, so I've just used the product rule to differentiate this product. Now I'm going to integrate both sides. Okay, so I'm going to integrate this side over here. Now, if we integrate this thing, this duv, that just undoes it, right? So I'm just going to get uv over here. Now over here on this other side, I get udv plus v du. In other words, I just throw an integral around both of those parts. Now on the left-hand side, notice all we have left is uv. And on the right-hand side, we've got these two integrals. Right? That's what we've got. That's pretty clear, pretty straightforward. It's hard to see any place I would have made a mistake there. That's all pretty straightforward. Now, here's what I'm going to do. I'm going to bring the integral v du to the other side, and on one side I'm going to have u dv equals uv minus v du. Okay? There, I've got that, right? So all I did was I just rearranged things a little bit differently than they were up here, where I have the integral of u dv on one side and everything else on the other. Okay. Now this is the formula. You can think of it as a formula that we can use for integration by parts, where we're going to view when we use integration by parts, what we do is we view the integrand as two parts, a u part and a dv part. So for example, let's suppose I've got x and cosine x. Okay? Now, if I wanted to find this integral, I would have a difficult time just knowing what I know now about substitution. So here's what I do. This is when I bring in this integration of parts, and this is a perfect one to illustrate it because it's a mixed types of functions, right? You've got a polynomial, and then you've got a trig function. Whenever you see mixed functions like that, you think, maybe integration by parts. So here's what I'm going to do. Now watch this in action here. I'm going to let u be one of these two things. In this case, the better choice is x. And you'll see why in just a second. So I'll let u be x, and then du is equal to dx. So now it's just like substitution. Now the rest, all that we didn't let u be, is what dv is equal to, which is cosine x dx. Cosine x dx. Now what I have to do is get the antiderivative of that. See? Because I want to know what v is. So v is equal to sine x, right? So I differentiate u and I anti-differentiate the dv, right? Does everybody see that? Okay, now remember how our formula goes. Our formula goes like this. We have uv right there, okay? So here I go. Here is u, v. See? Just from what I have down here. uv minus, now v, right there, du, which is dx. There we go. Now, we can certainly handle this integral, right? An infant could integrate this, right? The antiderivative of sine x, what is that? Negative cosine x, right? So here's what we've got. This is going to be x sine x minus, now, well, let me go ahead and do this, plus c. Okay? Because the antiderivative of sine is negative cosine. So then when you put these together, let's see if we can put them together. We've got x sine x plus cosine x plus c. And so that's what this is. Okay. Everybody see that? Yeah, it's related to substitution, but it's a little more than that, right? Because we don't just assign u, we also have a dv that we have to assign. So we're differentiating and we're integrating. Okay? Does everybody see that? Okay? Now remember, this comes in handy when we have, when you see mixed types of functions here, a polynomial and this trig function, for example, that tells you, I bet I'm going to be needing to use integration by parts. And remember, if you differentiate that, you should get this right back. Okay? Any questions? Now, this can get a little more complicated because we could have this. Now notice, let's just think about our choice for u up here. When I said let u be x, and I differentiated it, x was gone, right? I mean, it differentiated down to 1. So the derivative of x is 1. So that made it so that we no longer, when we came over here to the end with this integral, we no longer had anything in front of the sign. So that was easy for us to integrate. But let's suppose that we have this. Let's suppose we have x squared. And let me do something else in here. Let me just make this maybe a 2x. Okay, just so that I can illustrate two things. One, we're not dealing with a trig function over here, but we still have a mixed type of function right here, x squared and e to the 2x. Now, what we're thinking of is I want to differentiate this poor little x squared until it's gone, until it's just 1. That's what I want. So I'm going to do that. I'm going to say, well, let's let u equal x squared because differentiation diminishes the power of the polynomial, right? So then I have du is equal to 2x dx. Okay, good. Now, I'll let dv be the rest of it. Okay, like that. Now, you watch your bad self when you find the antiderivative because remember, you're dividing. You have 1/2 e to the 2x, right? You're not differentiating. If you were differentiating e to the 2x, it would be 2 e to the 2x, but you're not. You're getting the antiderivative. So 1/2, you divide by the 2. You see that? Okay, now once we do that, we go back through our process here. We've got uv, okay? So there's x squared and v is, well, let me write this. Okay, uv is going to be 1/2 x squared e to the 2x, right? Do y'all see that? That right there is uv. Now let me just make sure that's correct. Now minus v, okay, here's v, 1/2 e to the 2x, right? And du. So there's V right there, and then du, right? Everybody see that? Well, we don't need a plus C here because we're not interested in representing all the absolute values. We just need one. So we just need one absolute value. That's why we don't include the plus C. But that was a good question. But now notice that this 2 here cancels. Okay? So that was nice. We're glad that happened. But let's see what we have now. So let me just rewrite this just because what you want to do is you just kind of want to keep everything organized. We have 1/2 x squared e to the 2x minus this thing, x e to the 2x. Look at that. That's what we have right now, right? We went from this over here to this one. Now we still have a mixed type of situation here, right? We have x e to the 2x. So we don't know how to integrate that either, right? I mean, we're going to have to use integration by parts again, right? So what I'm going to have to do now, I've got to this point where I'm going to need to take this and do an integration by parts on that little fella, right? So you see, this can get involved. Imagine if this were x to the 5th. Man, we'd have a lot of work to do, right? Because then this would be x to the 4th, and then x to the 3rd, and then x2, and we just keep winding it down. This x right here, this x is from this one. This x right here, and this x right here are the same. Yeah. Okay, now, so what I've got to do is I've got to do integration by parts on that one. So, now I'm going to show you a shortcut here in just a second. But let's just look at this one right here. So I've got x e to the 2x. Okay? Now I'm going to let u1 be x. I'll call it u1 because, you know, we used u up there a while ago. And then du1 is dx. Okay? Everybody see that? Then I come back here and I say, okay, well, dv is the same as before. Okay? So let me just do that, and then v is 1/2 e to the 2x. Okay, everybody okay with that? Now, let's see what we have now. Now let me put this in purple just so that we'll see, okay, this was all a part of that thing up there in purple. Now, let me go ahead and evaluate this then. I've got 1/2 x squared e to the 2x minus, now I'm going to do this purple integral, right? Look at this. It's uv, right? uv, so this is 1/2 x e to the 2x, right? There's uv, the new uv, right? Minus v du. And that right there is the purple part. Right? Okay, does everybody see that? So this purple integral up here, this box right here, is this down here. And now we're at the point where this is easy for us because, okay, so now we've got 1/2 x squared e to the 2x. Okay, that's that. Minus 1/2 x e to the 2x. Okay, that's that one. And then this one over here, minus, now dig this, 1/4 e to the 2x. And now we put in the plus c because we're done. Oh, that's right. This is a plus. Thank you very much. Thank you. Woo! Yes, that's right. That was a close one. Thank you. Okay, any questions about that? Now, I've got the rest of the signs right. Is that correct? Okay, good.
What did you want to get to the 1/4?
The 1/4, I had this 1/2 out here, But then the antiderivative of e to the 2x is 1/2 e to the 2x. Okay, now you can see this would turn into a nightmare. If we had like x to the 5th e to the 2x or x to the 10th e to the 2x. I mean, we would have to spend the rest of our lives working through this. But let me show you, there is a pattern that happens. As we're working through these problems, there's a pattern that happens, and what we can do is we can use this thing called tabular integration. So let me go back and look at this problem from scratch. Okay, this is our problem that we had. Now, here is the answer right up here. We know that's what we were looking for. Now, let's see if we can just cut to the chase here. So I'm going to take this x squared, and I'm just going to start differentiating it. Okay? First derivative is 2x, next derivative is x, and then I differentiate until it's dead and gone, right? I just keep differentiating until it's 0. Okay? Don't pity it. It had a good run. It had a good run. Now, we come up here and we do the next part, e to the 2x. And what we want to do now is we anti-differentiate that thing until it's lined up down here with the 0. So, look at this. We've got 1/2 e to the 2x, 1/4 e to the 2x, and then 1/8 e to the 2x. Huh? What?
X squared 2x, would it be 2 or x at that point?
What's that now?
Or
On the
for
third
x
row, would
squared?
it be 2?
Yeah, wouldn't it be 2 right there
Third row
instead of
left
x?
side.
Oh, yeah, I'm sorry. That's right. That's right. Thank you. That's 2 and that's 0. I'm good eye. Good eye, Mike. Okay. Does everybody see that? Okay, now, yeah, and I was sitting here thinking, this isn't coming out right. But thank you. So now we do this. We do plus, minus, plus. Okay, notice diagonals. Plus, minus, plus. Do you see how those go? I mean, the way I've written it here, maybe I just go the next term down, right? Do y'all see how those line up? Now, this is what we do. When we want to write our answer, we're going to go x squared times 1/2 e to the 2x. So there's 1/2 x squared e to the 2x. Now, that right there was this. Right? Now we next come over here to this one. And it's going to be minus 2x times 1/4 e to the 2x. Right? And let me do a nice blue on that one. And notice that's a minus. So I put a minus there. Minus 2x times 1/4, that's 1/2. So that's 1/2 x e to the 2x. Right? That's the blue. And then finally, the grand finale, we've got 2 times 1/8. That's 1/4. See? So this one's, and it's a plus. So it's going to be plus 1/4 e to the 2x plus c. See? And that's tabular integration. So in other words, it's integration by parts, but it's kind of a shortcut, right? We just get right to the nitty-gritty and work it out, find the terms.
How does it work if there's 3 parts?
Well, this wouldn't work if there were 3. This particular technique wouldn't work.
Is there a technique that would work?
Not that I know of. Okay, so let's look at this. Let's suppose that we've got this. So let's suppose we've got x to the 5th, e to the x dx. And I want to so I made it kind of simple. Okay, so it's e to the x. So notice what we would do. We go x to the 5. I'm going to be careful not to make a mistake this time. X to the 4th. Now, 20, x cubed, right? 60, x squared. Ooh, 120. Man, I hope this ends soon. 120, and then 0, right? Okay, so that was a journey. Now we come over here to e to the x. Now I made it e to the x so it would be simple for us, just so that we'll see. What we would be doing, though, is we would be anti-differentiating this. But I just want us to see the pattern here. Now we've got e to the x, e to the x, e to the x. And of course, you know how e to the x is. Okay? And now it's just plus, minus, plus, minus, plus. And I guess this one would be minus. Okay? So then you can immediately see, now it's just a matter of writing everything down, right? So we would just say, okay, this is x to the fifth, e to the x, okay? Got that one, minus 5x to the fourth, e to the x, okay? So that takes care of those two. And then plus 20x cubed e to the x. Okay, that takes care of that one. Minus 60x squared. Okay. And then plus 120x e to the x. Ooh. I know, 120x e to the x. And then finally, the grand finale, minus e to the x. 120 e to the x. Oh, the grand finale. That's right. It's plus c. Okay, does everybody understand?